Good day. My name is Mark King, and welcome to Episode 7 of the Atlantic Canada IAH webinar series. My guest today is Tom Champion. Tom is a hydrogeologist with AECOM in Greenville, South Carolina. Tom has 35 years of experience. It's been my pleasure to work with Tom over several extended periods over the last 10 years or so. Tom specializes in resource development, remediation, and flow and transport modeling, and he's done a ton of drilling and field work and water resource development. Recently, he's been focusing on developing conceptual, geologic, and hydrogeological models, and that's going to be the topic of his talk today. Tom, how are you?
Pretty good. Thanks, Mark. I appreciate that. Yeah, you mentioned our long history. It is we've worked together quite a bit.
Yeah, we have, and it's been a real pleasure getting to know you and your team down there too. Worked with several of you down there, and it's been a good experience. So, what are you going to talk about today, Tom?
Well, we developed a base-wide conceptual model for joint-base Charleston weapons, and that's a little bit different concept over a lot of what typical environmental kind of assessment and remediation kind of projects tend to follow. There's no real regulatory requirement for this, but it came about that the Air Force, at least certain groups within the Air Force, felt that maybe there was a better way to understand the subsurface, and maybe understanding the subsurface was a little more important than just engineering remedies. And so we came up with this concept, and the base-wide CSM sort of thing is a more regional look. Instead of going site to site to site, we use the data from all the sites combined. There are probably 40, 50 sites on this particular property, and they've never been looked at except as one site and then another site. And so each one of them is very small, and if you look at it a little more from the big picture, it gets a little easier or you can understand the subsurface better. And so we decided to do this and had some success with it, and then continued. So we did this base right here, among several others.
Tom, people listen to these webinars from all over the world, so it doesn't say this on the introductory slide, so I'm just going to mention that you're talking about the U.S. Air Force. Maybe that's obvious, but just to clarify.
Thank you. Yeah, I don't get out much.
And probably there's some aspects of this that maybe that you can't talk about. So if I ask you any questions that you're not able to answer, just let me know.
Okay, appreciate it. Well, first of all, I have to tell you a little bit more about the project. We went in. There were probably 300 or 400 monitoring wells. I think there's been over 1,000 boreholes drilled on this facility. Most of those wells had not been surveyed to mean sea level. They used arbitrary datum, which is part of the philosophy of doing it site by site. There had never been a kind of synoptic water level measurement round across the whole facility. It's a large facility. It's over 16,000 acres. There are a lot of woods on it, a lot of difficult areas to get to, so that's probably had something to do with the way that they did it. We went in and, despite all that, measured all the water levels in every well we could find over a period of about 3 days. Put tide gauges in, transducers to measure tides, surveyed every well that we could find, and tabulated all that into a database, measured the depths of them, and kind of put it into an organized, base-wide kind of a database that could be used to facilitate future studies. So that was the field work aspect. We also did a little tide study, and I'll talk a little more about that in a minute. To give you a little background on the base, Joint Base Charleston consists of Charleston Air Force Base and Charleston Naval Weapons Station. Obviously, these were operated separately since one is a Navy base and the other one's an Air Force base. But there's been a recent move to kind of reduce costs, so they've come up with this concept of joint bases. So they made Joint Base Charleston, which is both of these facilities, and that is now run by the U.S. Air Force, even though the Navy operates it. And actually, as of now, this facility has Navy, Marine, and Army operations on it. So, consistent with the way the U.S. military does things, the only group that doesn't do anything on this base actually runs it. So, parts of this base have been in operation since World War I. This was an old Army base during World War I, and it's expanded. It used to be, during the Cold War, it was a Polaris missile. There was a Polaris missile base here and stuff like that. A lot of that's been closed down. A lot of munitions, though, are shipped from here or into or out of and stored, and there's a lot of material that gets shipped in here. Which brings me to where we are. We're on the coast of South Carolina, just inland a few miles. And Charleston is a pretty major harbor. It's the fourth largest container port in the United States. And the Cooper River, which is the larger river you see here in the picture, I'll try to move the little hand along it, is a pretty major container port. A lot of big ships go up and down this river, so this is a pretty major river. In fact, even these little tributaries that you see coming in are pretty extensive. Some of the things we call rivers up here, they don't even call creeks in this part of the country. It's probably 40 feet above sea level to lower than that, so we're not that far from the coast. There's a lot of marsh, a lot of swampland, a lot of kind of wooded areas. The southern part of the Cooper River is tidally influenced, but they built a dam, and you can see that dam right there. And north of that is not so much tidally influenced. The southern part of the Cooper River there is brackish water. The northern part is basically groundwater. It's more fresh. So the facility is divided up by a couple of pretty major creeks, Foster Creek here to the north and Goose Creek to the south. And I'll show you another picture here, a little bit of a topo map. Well, that just shows the surrounding area and the location of it. And actually, you can see a piece of property on the other side of the river. We didn't investigate that so much. And then here's the topo map. I might mention that this particular facility cuts across 2 counties in South Carolina, so Charleston, Berkeley counties. But this topo map shows kind of how the base, you can see the black is the outline of the base, black lines here. So there's a piece of it that's below the south of the Goose Creek. There's an extensive piece that's south of this creek to the north, which is Foster Creek, and a pretty big chunk that's north of that. One of the things we did during the course of this was look at precipitation, and we found that to be rather important. This is goes back to 1982. But anyway, the water levels out here are pretty shallow, obviously being that close to the coast. And so rainfall events are where you have rainfall that's pretty, if you're in a drought or you're in a real rainy period, can influence those water levels, and perhaps you measure your water levels in an unusual time and you might have different flow directions than you do on average. And we've run into that in some of these bases, and in fact, in one instance, the entire RI program was done, or the remedial investigation part of the program was done during a period of abnormally high rainfall, and the remediation was being designed during a drought, and the flow directions were all different, and nobody had kind of realized that they needed to account for that. So we looked at the rainfall. There have been some high rain events and some low rain events, but we didn't feel like we were too far off to make some conclusions about what our water levels looked like during our event. Besides these major rivers, there are an awful lot of wetlands, all these little blue blobs on this map up here and everywhere scattered all over that are wetlands. Even some of the pink ones are wetlands. Some of this is divided up by database source, but water is everywhere. During a lot of this, I made some assumptions that these wetlands were actually interconnected to the water table and that all the rivers were interconnected. I might also mention that this area up here at Goose Creek is in the intertidal zone, so water comes up in there at high tide. It's kind of an interesting topography, or a lot of wildlife around there too. So the geology and hydrogeology of this base, I looked at a regional scale. I might zoom in on this in a minute, but I think I went down to about 2,000 feet here. There's probably 3,500 feet of sediment, which is underlain by actually some volcanics that everybody thought was the end of the story, but I think here recently they think there might be some more sediment or sedimentary rock under the volcanics, and that has attracted some attention from the oil industry, but nothing really big at this point. This area was studied a little bit because there was a major earthquake here in like 1886, and so earthquake potential has been part of the issue. And so there were some fairly deep core holes drilled by the USGS and others. What I'd like to mention here is this, since this is 2,000 feet of column, we're dealing with about the upper 50 feet here. And underlying that 50 feet of sand, silt, and clay is something we call the Cooper Marl, or the Cooper Formation. It's not really a marl, but this stuff is really sticky. It's very tight. It's got phosphate nodules in it. I've drilled in this stuff, and it's very difficult to penetrate. They've actually bored a tunnel under the Cooper River through this marl, and they didn't even have to run a pipe in it. It's perfectly sound the way it is. Pilings are drilled into this stuff or driven into this stuff, and they just stop. So there's no water movement in the Cooper Marl. And the Cooper Marl is this green right here. And let me just zoom in on that a little bit. The marine formation, very tight. So that's the base of our shallow zone. The top of the Cooper Marl is the base of the shallow groundwater zone. There's really no communication between it and what's underneath. Underlying the Cooper is a Santee limestone. And that limestone is a pretty good aquifer. The upper part of it's cemented, so it's really a confining bed, the upper maybe half of it. And so it adds to the confining ability of the Cooper. But below that is pretty solution, and there's a lot of water in there. And underlying that is a formation called the Black Mingo. All these are marine formations, obviously limestone is. And the upper part of that is actually a pretty good aquifer. And below that it gets tight, and then there's PD formation, which is a clay confining bed. So this combined Santee limestone Black Mingo formation is the major drinking water supply aquifer for the area. A lot of people think that the Santee limestone is the northern edge of the Floridan aquifer, which underlies a large portion of the southeastern United States. There has been some saltwater encroachment in this aquifer, so deeper aquifers like the Black Creek down at the bottom here of what I'm showing are being investigated and used more extensively. The water quality is not quite as good, but you got to do what you got to do. So that's really the regional geology as far as it pertains to what we're doing. And so now that that's done, we can focus on the shallow upper 50, 100 feet of this. Actually, it's probably 50 feet or less, shallow aquifer. What we have at this base in this area of our South Carolina coastal plain is a series of marine sea level transgressions and regressions. And so what you see here at the bottom says modern transgressive barrier island system. This is a depositional model for a barrier island, typical of these parts of the coast. And what you have is a beach dune sediment here in yellow. And I'll follow this color pattern all the way through the document. You know, if it's yellow, it's more sandy, it's beach dune complex, it's high transmissivity type sediments. If it's brown or gray, it's part of the second part of this model, which is marsh and back barrier organic clays and silts. So if it's brown, it's going to be low transmissivity, typically back barrier. And then commonly in this model, you have a lot of back barrier channels, tidal channels that get cut and filled, and you have these sandy deposits back there. You can have sand lenses here back through as part of the overwash. That tends to pinch out as you move further into the back barrier, and that's fairly significant too to what we'll be talking about. In this part of the coastal plain, though, this beach dune complex is part of just a whole series of these type depositional environments that were formed as sea level moved back and forth, with the Surrey Scarp here being at 90-foot MSL. That was a Pliocene transgression, which was the last major one. Since sea level really hadn't risen more than about 25 feet, this shows that this area has been uplifted a little bit. And then as you step down, you drop down in elevation with each one of these terraces to the Atlantic Ocean. And Charleston Naval Weapons Station cuts across two of these kind of regressive, transgressive depositional environments, and there's also the depositional environment that is associated with the rivers and sediments and marshes that are being formed today. So that's going to form the basis of our kind of characterization of the subsurface as we go on. This is a piece of a geologic map And I'll zoom in on this more as we go through. But what I wanted to point out about this map is these purpley pink areas are beach dune sediments. And so the beach would have been going up this way, more or less to the northeast. And so what you've got here is what's left of this beach dune complex. Goose Creek has taken out a lot of it. And as you go up this way, then these areas here are back barrier parts of that model. And then you see some more modern deposition in there. Q3 and Q1 and Q2 refer to time periods. And so these are different back barrier sequences from different transgressions as Q2 versus Q3, etc. We got 3 sets of cross sections we did. One up here in the north, one in the central part, and one in the south. You can't see them real well, but I'll zoom in on them as we go. And one thing I should mention is these streams and wetlands, Foster Creek, Goose Creek, Cooper River, divide this facility into basically 3 hydrologic zones. And in this shallow aquifer environment, they really don't talk to each other too much as far as water levels go. There's too many discharge and possibly recharge surface water bodies, dividing them up for that to happen. So they're kind of isolated, and for that reason, we divided into this northern, central, and southern area. This is the result of measuring several hundred water levels. I drew this map by hand, and my eyeballs nearly fell out as I was going, but what it is, as you saw in the cross-section map, we don't have data everywhere. And so I use the elevations of the wetlands and surface water bodies, made the assumption at 40, 45 feet elevation or less that the water levels would be interconnected. I think that's true on probably 90% of this. There may be a few perched little water bodies here, but you got really what it boils down to some, an environment of islands and peninsulas. So we can see kind of an island peninsula type thing in the northern area. We see another peninsula in the central area and another peninsula in the southern area. So if you think about the way the water level should look, you'd probably have a divide running right down the middle of these peninsulas and groundwater flowing off to either side toward the discharge areas. And that's essentially what you have here, except that these water levels are kind of gnarled up by the various wetlands and little inlets and things that are all over the place in here. And what's left is this kind of a semi-radial flow toward little wetlands and surface water bodies, depending on where you are, all over the bays. These are all shallow water levels. There were some deeper wells, and I'll just show this real quickly. We didn't have enough of them, and I didn't want to make the assumption that they were connected to the surface water. These aren't really in a different aquifer as much as they are deep enough into the aquifer that I didn't want to contour them all together. But when you look at them, there's a little bit of a head separation there, probably just because you're going down through the aquifers. And the flow directions are about the same as in the shallow. You see the shallow map over on the left, and those little boxes there show you where each one of these little maps came from. And so this is another look at our cross-section. just so you can see it better, and there's some wells marked out in here. I'm not going to dwell too much on this, but you can look at where the data is and kind of tell where the problems are. But anyway, you can kind of see on this map where our cross sections are versus, and a lot of our water levels as they relate to these surface water bodies. So that moves us to working out, doing the first phase of this thing, really, which is working out the geology and understanding the kind of the subsurface architecture or the plumbing system that groundwater needs to move through. One of the things we do on these base-wide CSMs is we try to not focus on chasing plumes or developing water resources or anything like that. We just want to understand where the groundwater is and where it's moving and how it's moving, and then use this information however we can later on. Normally it's for contaminant to help with remediation and just overall understanding of the site, but these things can be used for other purposes, water resource development, potentially, depending on how they're done. And also, if there's any future spills or leaks, this gives us a good handle on how to go about assessing those if there's no wells already there. So that's part of the issue. And so what we want to do here is try to understand the subsurface depositional environments, and so what we work with here is litho-facies rather than so much lithology. We don't tend to correlate sand to sand, clay to clay by lithology as much as we try to correlate litho-facies. Litho-facies are packages of sediments that were deposited under various depositional environments. And so we try to identify those packages and correlate those. And these are the litho-facies we use. So we look at the yellow, which is clean, well-sorted sand that was deposited in back barrier environment. So these are going to be channel fills and flood tidal delta, washover sands, those type of sands. This other yellow one is fine-grained sand and silt, interbeds of silty clay, offshore shelf, back barrier lagoon, tidal channels. Those are the kind of things we're looking at there. Clay with silt, again, that's back barrier, channel, overbank, swamp. Clay, mostly pure clay. And that's probably the Holocene tidal estuary peat depositional environment that's being formed by these rivers that go through here now. There's also the Goose Creek limestone, which is a very small kind of transgressive or, lag type. It's hard to tell the difference between the transgressive lag and Goose Creek limestone, so we didn't try to. We just marked it out. It's very thin. It was detected in a few borings by other researchers, so we tried to include it where we could. And the gray here is the Cooper Marl, which will be the base of our study.
So, Tom, in practice, how does that end up being different to correlate litho-facies rather than lithology?
Well, litho-facies are depositional environments, and they have to occur within the same time period. So it kind of rolls in a little bit of a time stratigraphic approach. So if you were correlating sand to sand, you might not be cognizant of that, and you might correlate two sands that were deposited in very different time frames, which can't happen. So
okay, so you're going for litho-facies that have occurred during the same transgression cycle?
Right. And so the other reason, and probably the best reason, is With litho-facies, that really kind of allows us to predict what the material is from between boreholes. Since at most of these sites we don't have a borehole every 10 feet, you know, there's some need to make some sort of a conceptual prediction of what the subsurface is going to be like in between those boreholes. And the litho-facies and this type of correlation, which has really developed in the past 20 years, really. I think it started in the 70s with Exxon, but it didn't really get out into the public into the 90s. But kind of helps bring this kind of geologic assessment into a more predictive science rather than so much descriptive work. And so that's why we use it. It kind of allows us to predict things, kind of create a model of what the subsurface looks like to supplement those borings. Does that answer?
Yeah, it sure does. Thanks.
So keep that in mind. That yellow is also can be our beach dune type facies as well. So I zoomed in here, Q3, Q2, you can see over here. These are how they were classified on this map. Q2I is back barrier. And this, of course, is surface geology. These are our cross sections. There's a couple of places, one here that crosses a boundary on this map. We actually discovered another place that's not really shown. So these cross sections are pretty much in the back barrier until you get into these more modern sediments associated with Foster Creek. This is a cross section. Here's our litho-facies. This, I'll zoom in on this. These are grain size logs. So we go through the logs and assign a numeric code to the grain sizes, and they're shown here. They don't really stand out too much on this one, but they kind of let you visually see the depositional packages a little bit. If you have fining upward sequence, coarsening upward sequence, you can see that here if you've got some good logs. We also include the lithology. So we have a grain size log, a lithologic log here, and then we have our litho-facies that are correlated. And then we have various information about well screens and depths and so forth. Well screens, water levels. And if you remember, the brown is mostly clay, so what you see here, this is essentially clay. And there's a few channels cut into it. And as you move here, this is cross-section A. And if we go back, A is kind of running northeast, southwest. So we dip a little bit into this modern estuary sort of a thing here, and there's a little channel here, a couple of little overbank deposits, and then the rest of this is back barrier mud, Goose Creek limestone, and that was correlated based on some borings on other cross sections around here, and then the gray is a copper marl. So only a few channels here, a lot of interbeds. Nothing you'd really want to call an aquifer, in my opinion.
So are these channels continuous into the picture, Tom, or are they quite isolated by the mud?
I think they're going to be kind of isolated. They may meander a little bit, but I don't think they're terribly extensive. Here's another viewpoint. This is BB prime, which cuts across that at right angles. And it also cuts down into another back barrier depositional environment that's a little more sandy and is a more modern. So you could have some interconnection here between these little channels as you move down into that, but you see kind of a stark kind of transition there, which we believe this channel right here was eroded away and that was deposited. Again, the Cooper, a lot of interbeds. So it's likely that if there's water moving in these little channels, they're going to intercept some wetland or some little surface water body at some point, would be my guess. So then we zoomed into the water table here. And I think if you recall that these are all wetlands and surface water, or places where the groundwater is close to the surface enough to sustain a wetlands habitat, you can see how complex the groundwater system is. And then I've zoomed in on a couple of areas where we've got monitoring wells. There's where we are on the base. There's where we are in the world. One of the things that strikes me about this is if you have a recharge event or a drought and these water levels change, you know, the vectors off these areas here, the groundwater flow vectors can change depending on the recharge, so that your ultimate receptor or discharge point is going to be maybe a different wetlands under some cases than others. So I could see these vectors kind of swinging around in an arc depending on whether you're at low or high kind of water. But the overall high versus low would kind of remain like it is. So I did just a Darcy calculation using some slug test data that I found in the record, and I didn't pick the average so much as I kind of picked what I thought was representative based on the cross sections. And you see it printed over there. If you take a 1,000 foot long strip, I think I used about 35 feet. Yeah, 35 feet for the aquifer thickness, which is on average pretty typical. And the gradients are all over the map, but you know, I kind of picked one that looked reasonable off this map. Came up with a flux, groundwater flux across that 1,000 foot strip of 0.35 gallons per minute, 500 gallons per day. If you pick a different kind of a gradient and change the parameters a little bit, you can get up almost to 3 gallons a minute depending on where you are. But I don't think that qualifies as much of an aquifer if you're going to try to have a well in it to pump. So I'm thinking not really an aquifer. This is the central area. There's the cross sections. We're still mostly in this back barrier, but there's a little more coming in here from another back barrier deposition, plus the Holocene river deposits. And we've got a string of cross sections running kind of north, west, southeast, and then cutting across there at right angles, more or less. And so CC prime takes us into a back barrier deposit right here, which has been called a 10-mile formation. A lot of variability in the literature as to what these formations are really called. But this part of the the system is, as we're moving, we've kind of slid over to the southeast from where we were in the northern region. So this part of the system is closer to the shore face, where you have the coarse sands and medium sands, clean sands, aeolian sands, beach dune sands. And so we see more overwash, and so this is a bit sandier than what we saw in the previous cross sections. But then we hit this back barrier deposit here, which would be on the further away from the shore during that depositional environment, and it would be mostly clay. So where you are in the depositional environment makes a whole lot of difference as to whether your formation is going to be transmissive or storative in terms of contaminants. You know, this might be a storage zone here in the clays. This might be more of a transmitting zone with some storage zones in these interbeds. And so still, it probably isn't much of a water supply aquifer. Anyway, I move on. I think I'll move on. Okay, this one's pretty much in, this one's running east-west, and this is pretty much in that back barrier area that's close to the shore face. We can see some scour cut out here in the Cooper Marl, a little sand channel here at the base of it. A lot of little interbeds. This is a pretty interesting one, I think. This shows you kind of dramatically, I believe, how crossing one of these depositional boundaries can abruptly change what the subsurface is. So we've got these lagoon sands and overwash sands, maybe even some delta in here, delta channel deposits coming through here. Down at the bottom where the big yellow, you can see a little bit more here about our grain size logs. I don't know if you can see that yellow one, but you know, that indicates a pretty good sand right there, a little bit of a fining upward sequence. And then we get right here, between these two borings, this is where we cross the boundary on the geologic map. And then we get down here and we're in the mud that's cut up by little individual channels in these back barrier lagoons. So if you remember my depositional model, we would be on the left-hand side of it with all clay cut by a few little channels. And that's what we see right here. And that, you know, when you look at the water levels up closely, some of these levels really show that certain channels are isolated from certain other ones because they don't make a lot of sense when you contour them otherwise. And this is possibly one of the most complex ones of the whole thing. This is just very back barrier mud cut by these little tidal channels, a little scouring into the Cooper. If you had a contaminant site here and you wanted to remediate this would be kind of complex. Rarely do we get enough geology and borehole data to actually map all these things. So there's a lot of interpretation here, but this is probably about what it looks like. Nope, it actually changed. Okay, now we move into the southern area. And what we do is we're going to cross this back barrier. This is an interesting cross section here to me. Cross this back barrier, go across the Goose Creek intertidal zone and into the beach dune facies. Then we have a cross section completely in this beach dune. Oh, I should mention on the previous, in the central area, let me just back up. Sorry about that. The same calculation, a flux of 1,000-foot long strip at typical conductivity is about 8.6 gallons a minute. Not quite 9,000 gallons per day. So a better zone here. Probably gets real clayey back here, but not a great aquifer. And so then we'll move on to this unit, the southern area. This is our G prime, which runs right through this beach dune facies. Sorry. Looks entirely different from the other ones. This is all sand. This top part is wind deposited. The middle and lower are shore face sands. These little clays here, or these little cat's eye formations. These are little inlets that were there and that got planed off during the deposition. We see a little bit of the Goose Creek limestone in here, or probably really what most of this is a big basal lag as this thing was being deposited, and then the Cooper formation. So this is all mostly sand. It gets a little bit cut up as you move down the column, but with a shallow water table up here, you've got a lot of aquifer here. This is the cross section that crosses from the back barrier across Goose Creek estuary into the back barrier of another depositional environment, and then into the beach dune facies of another transgressive regressive sequence. So on the left side of this thing, we have beach dune and wind-blown deposited sands here. This would be on the right-hand side of my depositional model. And then the Goose Creek limestone and one of these little cat's eye things here, and then the Cooper marl. And so this is pretty clean sand. It's been eroded away by this transgression here with these back barrier sediments. And then that's been eroded away, and this contact is based on the geologic map and the topography and everything else like that. There's no boreholes here to define it. But this is the estuary deposits of the current system, and this is the back barrier of another transgression. So there's back barrier, this is back barrier of one transgression, back barrier of another transgression, beach dune of a third. And then you have this more modern Holocene deposit in here where we think it's scoured out. Well, it's definitely scoured out the Cooper because we've got boreholes over here to show it. So keep in mind as I talk a little more, you've got these wells over here that are in this estuary deposit, and these wells over here in the back barrier. And there's some interesting hydrology going on there. So from a geologic standpoint, how much you're going to be able to transmit both water, contaminants, and how much is going to be stored in terms of contaminants depends really on where you are in this sequence and in this depositional environment. And it's possible to predict and define what these are, with some reasonable assuredness. This is just another little back barrier cross-section. This is some additional data that we had showing the scouring of the Cooper in that area. This is a far back barrier with some channels. This is slightly closer to the shore face. And this is the southern area water levels discharging strongly toward the Goose Creek. But you see our kind of divide coming in here. Again, these sites, the vectors can be very complex depending on where you happen to be standing at the moment if you're on these sites. I'll just zoom in a little bit on this little area down here. So you can see that just depending on where you are, groundwater could be going any number of different directions, except possibly back toward the high topography. So we did tidal studies, and this dotted line is the Cooper River. So there's about a 5 or 6 foot tide, 6 foot, coming up the river. And the monitoring wells on this side are right by the river. And so they have about a 3 foot change as the tide goes in and out. Not really a great deal of lag either. These are little shallow wells. And so we did that at some other sites. This one's more back away from the river, and we don't see any influence too much of the tides. However, there was a rain event during this thing that shows right here, which, if you go back, interestingly, it's hard to find in this hydrograph. We have transducers and wells scattered around in different environments just to kind of see how the water levels responded to tides, and also understand how to interpret the water levels at the time we measured them. These are the two areas that were right next to one another. This is the Cooper River again, this dotted line. This group of wells right here was in the estuary kind of sediments. You see a pretty darn good tide influence. Not so much of the rain event, maybe a little bit. These wells up here were in the back barrier deposits, and the wells are literally just about across the street from one another. They're not very far apart. You see very little tidal influence and a huge, well, you might call it huge, you can see influence from the rain event. My interpretation is you've got nothing but clay here, so the water levels kind of act like they're a little bit confined. Up here it's more sandy, so we get some recharge coming in, not in the tidal impacts are kind of damped out. So that's an example of how the hydrology and the geology, really depend on one another in terms of how the whole system works and how you interpret that and how you deal with it. And then these are just some observations that I don't want to repeat all this, but you've got these major creeks. You've got really 3 hydraulic areas. You've got, I might, before I go on, mention that this area has my calculation in the beach dune sediments for aquifer material flux across a 1,000-foot long strip was ranged from 40 to 60 gallons a minute. So that's the major aquifer. And that aquifer is used. And it strikes me in terms of contaminant cleanup that the major aquifer is also the easiest one to clean up. There's less clays, less heterogeneity. It would be conducive to lots of different kinds of strategies, but some of the ones in the back barrier sediments would be more difficult, and they really aren't drinking water aquifers. So perhaps that's usable for some planning in the future. And there's a lot of organic material in the back barrier sediments, so that probably should be taken into account. And that pretty much concludes what I had to say. Mark? I think we've covered most of the ground here.
Yeah, an interesting approach that you've developed to generate a cohesive conceptual model of what appears to be a very complicated setting. I can appreciate that there must have been a lot of head scratching as you were starting to build this story and about the most appropriate way to lump and group and split up these materials. But can you? I'm not sure how much you can say about this, but can you tell us what you concluded with regard to remediation of the site? And you didn't say anything, and I can appreciate that you probably can't say too much about the contaminant distributions and whatnot, but just in general, can you tell us a little about what you concluded about approaches for remediation here? And I take it that was the original purpose of the conceptual model, was to support ultimately remediation?
Yeah. Unfortunately, that's under, well, I don't want to go there, but I guess the main thing is you can look at these depositional facies, and I think the National Academy of Sciences National Research Council published a book not long ago about complex groundwater sites. And if you think of it in those terms, as to what would constitute a complex groundwater site. I know ITRC, is the Interstate Research Council, is working on a guidance document about complex groundwater sites. I've done a little work with that committee, and it's a very hot topic, and there's been a lot of debate between regulators and private regulators, consultants, and private entities, and the Air Force and the Navy and the Army and the oil industry, and it's kind of a controversial topic. But if you think of it in terms of where the complexity is, what would be a complex site versus a more straightforward site, you can look at these depositional facies and the way the water levels look and whether it's tidally impacted, and determine the degree of complexity. And I think you could use that to say, okay, if I'm in one of these more complex environments, do I really have enough information to design a remediation? And what kind of a thing should I put there? And what should I expect as a result? I think you can come up with those kind of conclusions from looking at this stuff. It won't tell you whether to use chemical oxidation or biological degradation or any of those, or pump and treat or whatever, but I think you can look at what kind of level of effort it's going to take, whether you've got enough information, and make some decisions about how you want to approach it in the long haul. So I kind of looked at it in terms of where the complexity is versus where it would be fairly simple. And that goes back to a lot of the complexity is in the areas where you really don't have a drinking water aquifer. Though you may have some wetlands or something like that that might be a receptor. And maybe you can look at those kind of issues around those more complicated ones. So I think that's a good way to use that.
Mm-hmm. And when I look at some of your early slides that show the land itself and the distribution of wetlands, et cetera, it occurred to me that early on, I guess early in during the development of the base. What did this land look like? I mean, was it difficult to settle? It looks like it would even be very difficult to get into at some stage before roads were built and things like that. What did it look like? Was it settled originally before the base, or was it just kind of impenetrable?
The history of this area goes back to about 1680. So Charleston was one of the original, kind of one of the early settlements of the Europeans that came over here, and Charleston itself, downtown, of course, right on the peninsula, and this area here would have been considered a backcountry. So people gradually started settling it, and then there were a lot of settlements here where people, boated. And one of the cool things about this area, with the digging of a few dams here, a few canals that were real short, you created this intercoastal waterway that people could navigate from North Carolina to Georgia by boat without actually getting out in the ocean. And so there was a lot of movement along these little creeks and rivers, and they were laden with fish, and there was game everywhere. So the settlements were crude. As time went on, Charleston basically expanded out quite a bit, but there had to be a lot of, trees cut, filling, a lot of ground filled in. I think there's been some filling, like up here on this peninsula right here. I think a lot of that, I'm not 100% sure, but it looks like to me some of that ground's been built up. I think people, when they were looking at developing this base, were willing to do whatever was necessary to get access to being able to use this port here. So if it needed filling, they filled it. So yeah, I think it would be difficult. And there are some areas out there that are difficult to negotiate now, even on foot.
Right.
You don't have some real mud boots on, you're just going to sink up to your hips.
Huh.
And of course, we picked the worst time of the year to do this, so everybody got all sorts of bug bites and that sort of thing when we were actually out here. If we could have gotten out in the spring, it would have been beautiful. But instead, we picked the hot
chiggers.
Yeah, chiggers. One person had 70 chigger bites.
Nice. Well, Tom, thanks a lot for an excellent presentation. It was really interesting to see the thought process that went to consolidating this information and making a story, a conceptual model out of it. Very interesting.
Thank you.
Thanks a lot, and hang on, and I'll catch up to you, and we'll have a little chat. But I'm going to click off the recording portion of the presentation here.
Okay, well, thank you.
A lot, Tom.
Appreciate the invite.